Hello. Hello, Angela. Can you hear me? You are on mute.
Yeah, hi everyone.
Yeah, hello everyone. Okay, let's start our meeting. Let's start our paper reading class. Hello everyone, good evening, and I am Kainza. I will be the host for our today's session. So, let me check. Okay. Yeah. So today's session is Women in AI APAC Machine Learning paper reading class, and this session will be the week 3 or our session. So in our first two, we did two events in previous week, and this week we bring at the paper introduction to ROC Analysis. So this event is hosted by the Women in AI APAC chapter, followed by the guideline or Google Machine Learning community. So before starting our session, allow me to introduce a little bit about the Women in AI. So Women in AI is a non-profit student working toward inclusive AI that benefit global society. So we are founded in 2016, and then now we had over 8,000 members across 140 countries. So today event is hosted by the collaboration across the APAC chapter. So today we invited our speaker from the Australia chapter. And so we are planning to host total 10 week for our machine learning paper class. So we did first two. In our first week, we did some orientation and we invited speaker for the keynote session. And then in our second week, Women in AI in Philippines chapter hosted the paper Zero Shot Learning through cross-model transfer. And this week, we plan to introduce about the introduction of ROC analysis. And so in this, we invited Angela. So let me introduce a little bit about the Angela. So Angela is data analyst, writer, data analyst and AI, and also she is a Women in AI ambassador for Australia, and also she is a chief education officer of Women in AI global team. So she is an AI professional specialist at the bias, ACI, and diversity and inclusion in AI, and also she is recipient of Doctor Analytics Lead 2020 from the Institute of Analytics Professional Australia. So, Angela, thank you so much for hosting our event, and it's really our pleasure to be with you. So, over to you, Angela.
Thank you so much. Thank you, Kanza. It's such a always pleasure working with you and also working with the amazing Women in AI APEC team. So by the way, Kanza did an amazing introduction around what we do as a Women in AI, but we have chapters in Australia, Japan, Myanmar, Taiwan, Singapore, and Malaysia and India. And we are about to establish, Hong Kong chapter as well as Korea and also Vietnam. And in the early 2023, and also we are looking into expanding into Nepal and Bangladesh and other regions as well. So if you are interested, please feel free to reach out to Women in AI APEC team or Global Women in AI team as well. So kind of did a really kind of introduction, but I am a data scientist, and the reason why we believe in this is very special journey working for Women in AI is women helping women. I'm not saying that we are not helping men, but as you know that there's diversity and inclusion issues and gender equity problem as well. So it is very important, and when women are helping women, it becomes more powerful. So why don't you really take the journey together with us? There are always the roles you can help, and you can. It's amazing work. I've been working with the kinds of nearly 4 years now, and we really love enjoying working together. And next year in Australia, June, we will have Women in AI APEC Awards. This is special really event, and we've been running Women in AI Awards Australia and New Zealand in the past 2 years, last year and this year, and it's been very successful. So each year we've identified about 160 plus women, female AI researchers and professionals on all different the categories, like AI in health, AI in manufacturing, AI in diversity and inclusion, AI in law, AI in creativity, you name it. So all different categories, and we try to identify females and celebrate their work and nominate them and really acknowledge their work, and we give the prize as well, and we celebrate together. By doing that, we can really promote all this amazing work women are doing, and also we can show example to the next generation what women can do, and the sky's the limit. We can really remove the glass ceiling, and that's why we are working together. So kind of did a really amazing introduction, and I think we can continue talking about women in AI in the next session. But why don't we actually switch to the ML club, the topic we want to focus. So Kinza, would you mind if I can, share the screen? Is that all right?
Yeah, I think you can share your screen. Yeah.
Thank you. So see if I can share the screen. So can you see my screen?
Yeah.
Yep. Cool. So guys, before I start, my name is Angela Kim, and I hope you have access. Can you please maybe share the link
Yeah,
on the chat?
I have already shared to the
Fantastic,
other
fantastic.
participants. Yeah.
Thank you so much. So today's the topic is an introduction to ROC analysis, right? So ROC is we often abbreviate it and call it ROC analysis, right? The reason why it's so important is there's a high application that you use for model building, especially when you talk about the confusion metrics. So ROC stands for Receiver Operating Characteristics Graphs. And the reason why ROC graphs are because we are talking about this particular graph here. So this is the straight line that false positive rate and versus the true positive rate. But when you talk about ROC curve, we often talk about this kind of graph to the left, and then this is very stepped approach because we are talking about very sample about 20 odd the sample instances. But in a real world, and if it's not discrete distribution, you might often have very smoothed out curve like this, and it's called the ROC curve. And the reason why it's very important is because ROC curve gives you the opportunity to consider how different decision making can be made, and how would you decide balancing how much do you want to actually you are willing to give as a force positive and negative in that scenario. And the reason why people talk about it's often used for medical decision making is because this decision tree kind of related the and also discrete true or false, yes or no kind of decision making. There are so many the health related, medical related use cases used, and often it was cited for the using application of ROC curve and ROC graph. And that's why people often find it from healthcare and medical use cases in the research paper as well, and this is one of them. So why don't we maybe deep dive into, let's start from the intro part. So probably you might have opportunity to read through and the people who's attending now didn't have opportunity to read through this paper. It's okay, because what we are going to do today, what we are focusing today, is going through the important characteristics of the background of ROC, the graph, and why we are using it, and why it's important when you talk about the machine learning, and what's the practical the application it is, and some tips and tricks of when you use it and how you use it. And the reason why it's important is because the confusion metrics concept itself is quite new, and it's not very easy to digest, especially for the people who's getting into data science and AI field as a new learners. But if you're experienced, rather from work experience or some experience in the research, then you are quite familiar about the confusion metrics and what ROC cover and graphs actually indicate and suggest. So as mentioned, it is used for visualizing and also organizing, selecting classifiers based on the performance. Performance meaning the score, ROC score, the performance score you're talking about, right? So it's been around long, it is not like a new concept. It's been around many years, like more than 20 plus years. And the reason why it becomes more popular these days is because the classifier performance feature. And also it started from the old days, like when I was actually, at university. I remember some professors actually plotting the ROC, curve using Excel and, putting the numbers, and actually it can create the, actually the smoothed out curve, right? But now it's been changed. So, you can use, Python coding, you can use R, and you can automate, creating the ROC curve with the scripts. So let's go into more details about the intro part, about how it's used for visualizing and analyzing behavior of diagnostic systems, which is like medical decision making situations. And the reason why it is very popular was because, again, it's often deals with the discrete the distribution. And these days, of course, it's not just limited yes and no discrete. It can be applied to the continuous, the situation as well. But majority of use cases still coming from discrete use cases. And you can see that the why it is being used is because the characteristics and the characteristics of how cost sensitive learning and learning in the presence of unbalanced classes. So ROC graphs are there are non-obvious complexities when you use it in research, and this particular research paper and article really try to address the basic introduction of ROC graphs and guide using how it's been used in the research. And also the goal of this article is to really general knowledge about the ROC graphs and how to plot, promote, to evaluation practices in the field. So let's move into classifier performance part. So as you can see that this classifier performance, the section introduce you to the mapping of the, how it's, like mapping into element set, P and N is, so it is like, when you look at this one, you can see that the, how true class and versus, hypothesized class, right? So which is predicted value. So when you look at, yes and no, and true positive and, false positive here, it is slightly confusing. So why don't you let me quickly paste. I found, actually, I often use better diagram, which can be actually found from here. Let me paste into, I think I can grab this one here. So why don't you can you see my screen?
Yes, we can see.
Excellent,
Yeah.
excellent. So rather than the graph used in the article, I found that actually this particular diagram is much more straightforward in terms of understanding, very with a very clarity. So as you can see that when you talk about the ROC curve, you need to be very familiar with the confusion matrix, and to understand confusion matrix, you have to understand how this diagram works, which is predicted conditions, right? So which means the model creates the predicted condition versus actually the case of the actual condition. So you are left with this 4-dimension for the quadrant, the box that you need to create based on predicted condition, which gives positive. So positive, but this is positive total population of positive and negative, right? But this is giving predictive positive and predictive negative, which means the model gives out what the outcome look like versus the actual positive case and actual negative cases. And once you define the x-axis and y-axis of this the framework, then depending on the situation, the model predicts true predictive positive, but actual the condition is positive, then we call it true positive. And on the other hand, actually predicted is negative, right? But actually is positive, then it becomes false negative. And the other way around, when actual is negative and the model is predicting positive, it becomes false positive, which is the pink on the bottom to the left-hand side, FP as an abbreviation. And also, when model predicts negative, but actually it is actual is negative, then it is true negative. The reason why it's important is because based on this true positive and false negative and false positive and true negative, you can calculate very important scores, and the total population is made of between the positive and negative, obviously, right? So let's go back to the paper. So basically this is the same story, but once you realize a predictive is a true class, predictive is actually hypothesis, and true class is a true class, then you can understand to calculate false positive rate, it is based on the whole population. you are giving what is false positive. Same goes to true positive, right? Based on true positive population, you are calculating what is true positive rate. Now, the precision, which is very, very important, and it is all about the precision and recall, as you know that. The reason why it is all about precision and recall is there's nothing wrong or right decision. There's no cutoff threshold that we are deciding. Rather, once we create the ROC curve, depending on the business appetite, how much they are willing to lower the threshold or higher the threshold, you can use how much you are giving for the precision and recall. And from this diagram, the way you calculate, obviously, once you understand this diagram and how it's been calculated, of course, it can be coded and scripted, and it gives out the value automatically. And the precision is true positive rate out of true positive n plus false positive, which is this true positive and false positive. So, and then other recall rate is true positive over positive population. And the accuracy is positive plus negative is the whole total population. And then you are adding true positive and true negative. And F-score measure is 2 over 1 over precision, which is this one, right? True positive over true positive plus false positive plus 1 over recall, which is true positive over positive. So this is confusion matrix and common performance matrix calculated from it. Why it's important? Because it's all about deciding which point on this, the line, are we deciding to balance between false positive rate and true positive rate. And this section is actually just to elaborate what we discussed in this diagram, which is, again, it's repeating, like true positive rate is positively correctly classified versus total positives, which is this one, right? Total positive rate gives total positive over positive rate, positive total positives. And again, this false positive rate is negative is incorrectly classified over total negatives. That's a false positive rate. And again, sensitivity is recall, and specificity, which gives often by the script, is true negatives over you combining false positives and true negatives, which is this value. Yep. And so positive predictive value is precision, and this is how you plot. When you versing false positive rate and true positive rate, and you're drawing the diagrams, and there's this graph here. This example is actually giving just the 20 sample use cases. And when you use just 20 sample cases, it doesn't give a smooth graph. Rather, it gives the stepped graph depending on the coordinates it's giving. So which is again the same true positive rate and false positive rate. So let's go back to the narrative around why it's important here. Okay, so this part, actually this from here, this part is describing why ROC space is important and how it is described using this false positive rate and true positive rate plotted and putting the diagonal, the line. So on the diagonal line, this is the model performance. It is used random without predictive model. So which is performing above is better off than random selection, and underneath is actually the worse off, which normally wouldn't happen. So when you look at the graph with a two-dimensional graphs with true positive rate and the false positive rate, and it is the graph depicts the trade-off. As I mentioned, balancing and how the business is deciding which benefit to give with a cost. So there is, again, no right or wrong answer. Rather, is business is willing to give, accepting more benefits by providing, or at the cost of more expenses costs. And it can be sometimes different cases. If you can't afford this cost, you go less cost, but that means less benefit as well. So it is giving the decision to the business decision makers, but data scientists, engineers, data analysts actually providing the raw covering the graph, giving how much appetite, sensitivity, how much decision making, how much benefit and versus cost, the trade-off you can actually offer by giving this graph of raw curve. And again, it's talking about, normally it's discrete classifier. Doesn't mean that it's only discrete classifier, but often a lot of use cases just discrete classifiers. And it is talking about how again the graph, you can give this the straight line gives the random, the selection, whether it's without any the predictive ability applied using the model, then it is where on the line, but normally it should be better off. So when you look at the rock graph, you might think it is a label, they make a positive classifications with evidence, but actually, and also the first positive rates, but it is not true, because many real world domains are actually dominated by large numbers of negative instances. So the performance in the far left hand side of the rock curve becomes more interesting. It is something quite interesting to note. But let's go back to the random performance, the narrative, because it's very important, because it is often used to explain to the business why the model is outperforming. Because to prove that model is outperforming, you have to give the random performance, which is the often described as the straight line, diagonal straight line. So this diagonal line y equals x, which is this one, right? So we are talking about the random, the performance. For example, the classifier randomly guesses possible class half the time. It can be expected the negative is correct. And it gives 0.5, 0.5 in ROC space. And then if it's above, then 90% positive. And then it's giving 0.9, 0.9 in the ROC space. And again, it can be lower than 0.7, which gives 70% of the time. So when you look at the diagonal is a random performance. Below is actually said to have useful information, but it is applying the information incorrectly. So given a rock graph that classifies the performance appears to be slightly better than random, then it is natural to ask, actually, is it truly significant? Or is it better than random by chance, right? So there's no conclusive test actually showing, but there are some techniques you can use to apply rock curve better, and also presenting to the business how it can be actually very useful. So again, let's moving into the next the section in this paper. It's talking about a lot of classifiers actually using, for example, decision trees. So it is either yes or no, very discrete class. And when you talk about discrete classifier, we are talking about the single confusion matrix, right? And which is actually we are talking about the point and produce the single point on the rock space. As a result, it might look like very stepped, the stepped up, moving the curve rather than curve. But in the real world, we can actually graph it continuous the curve, and it can be capturing not just a discrete rather than continuous variables as well. So when you talk about the relativity, so this one is actually talking about how the sample of 20 use cases, and then how it can be graphed as a stepped approach. And also when you move into figure 4, which is I believe figure 4 is this one. Actually, this figure 4 is on the below, this one. So you can see that how the class scores and classification, the 10 incidents, and can be graphed, and actually it can be scored, which means this case it has only 10 and this particular applicable scores, but actually it can be drawn continuously as well once you decide to have a bigger, much bigger sample and smooth it out. So the important about the ROC curve application, I'd like to address about the creating the scoring classifiers, which is quite practical, and this is very the relevant the use cases as well. So many classifiers models are discrete, but as mentioned, but actually it's designed to produce only the class label to test the instances. But again, we can actually generate the full ROC curve from classifiers instead of just a single point. And to do that, we can just run the model to use to show how smoothed out the graph, and each the points on the graph is the scores, and all this continuous the continued the score collection actually shows the all this possible the choices of benefit and cost, which means depending on the threshold the business choose to select, you can give how much benefit it can earn by sacrificing the certain amount of costs, which can be normally the cost can be anything. The cost can be the time, cost can be actually dollar value, and cost can be any the quantity that actually you are giving in to obtain the benefit in the context. So the combination of the scoring and voting. So voting here means the class level voting and generate the score. And this one is actually employees begging to generate ensemble of these discrete classifiers, which produce a vote, and that can be used to generate scores. And some combination of scoring and voting can be employed, which can be used in this weighted voting use cases in this paper. So efficient generation of a ROC curve component is that's part, actually it's quite practical and useful. So given a test set, we often want to generate ROC curve efficiently from it, and we can exploit the monotonicity thresholded classification. So any instance that is classified as positive with respect to given threshold can be classified as positive for low threshold as well. So when you move into how the F scores and move down to the list, processing instance can really updating the true positive and false positive as we go. And in this manner, ROC graph can be created from a linear scan, which means it can create actually the continuous variables. And the algorithm shown in algorithm 1 TP, true positive and false positive, both start from 0, obviously, go up to the incremental value until every negative instance will increment to false positive, and maintain stacking over the actually the R of R is the percentage of the model accuracy and ROC points. So pushing a new point onto R, and instant is processed, and then final output in a stack of the R, which will contain the points on the ROC curve. So when you look at this the graph, there's actually graph describing here, right? So this figure 6 is again how describing the false positive rate versus true positive rate, and on the graph how it's expected as this on the line, and pessimistic when it's under, and optimistic as when it's over, because you can see that this random line, this is random line, right? And this is model performance, right? And the above is optimistic and below is pessimistic. So let's move into the next section where it explores about the model, the calculating the area under the ROC curve. So this is important to address actually the area under the ROC curve. as it's explaining here. So consider decision tree containing a leaf node accounting for n positive and m negative. So every instance that is classified to the leaf node will be assigned to the same score. And the rectangle of figure 6 will be size of nm over pn, and that's a multiplication of nm and over pn, and that's averaged to account for the errors in the ROC curve as high as nm over 2pn. So actually, let's have a look at to the next the graph about the area under or ROC curve or AUC, the value. So the ROC curve is a two-dimensional depiction of the classifier performance, as we discussed earlier. And we talked about why it's important to actually to mention and to understand clearly about the area under our curve. To compare classifiers, we want to reduce ROC performance to a single scalar value representing expected performance. So the common method is calculate the area under the ROC curve, and it's often used as a AUC, the value. Since the AUC is a portion of the area unit square, so its value will always be between 0 and 1.0. So it's between 0% to 100%. However, because the random guessing producing is a diagonal line, which is between 0 and 0 and 1 and 1, and which is 0.5, 50%. So no realistic classifier should have an AUC less than 0.5. So AUC has an important statistical property, which is the AUC of classifier is equivalent to the probability that the classifier will rank a randomly chosen positive instance higher than a randomly chosen negative instances. So this is equivalent to the Wilcoxon test of ranks, which is quite popular. The score you use, and again, all these scores generated by the coding scripts, and AUC is also closely related to the Gini coefficient, which is very, very important when you talk about the randomness and when you talk about diagonal, which is the random line, and the ROC curve. So it's kind of formula used, right? So Gini plus 1 becomes 2 multiplied by AUC value. So as you can see that the figure 8a shows the area on the two ROC curves, which is this one, right? So these two ROC curves I'm showing false positive rate and true positive rate, and this is false positive, true positive rate. And when on the line, so this graph is showing the area under the ROC curve, and the graph on the right shows the area under the curve over discrete classifiers and the probabilistic classifier. So let's have a look at this part, which is the narrative to explain the graph. The areas under the two ROC curves A and B classifiers, these use cases, right? And the greater area, therefore better average performance. Hence, the figure 8b shows the area under the curve over binary classifiers. And A in a scoring classifier, B classifier, A represents the performance of B when B is used with a single fixed threshold. So the performance of 2 is equal at the fixed point. So it is possible high AUC classifier to perform worse in a specific region of a ROC space, and a low AUC classifier can actually perform higher, can show higher the performance in a space. So when you look at the B, generally better than A, except FP rate is greater than 0.6 we are talking about here when it's actually crossing here. So when you look at averaging ROC curves, it's important because although ROC curves may be used to evaluate classifiers, the care should be taken using them making conclusions around the classifiers' superiority. Which one is better, right? So some researchers assuming ROC graph may be used to select the best classifiers simply by graphing them in ROC space and seeing which ones dominate. And it can be misleading because analogous to taking the maximum of a set of accuracy figures from a single test set without the measure of the variance. So we cannot compare the classifiers. So averaging ROC curves is easy if the original instances are available and given test set generated from the cross-validation or bootstrapped method. And we can simply just merge sort the instances together by their assigned scores into one large test sets. Then we can run a ROC curve generation algorithm, such as algorithm on this point to plot the result. And then ROC space is two-dimensional and any average is necessarily one-dimensional. So ROC curves can be projected into single dimension and averaged conventionally. And it leads to questions of whether the projection is appropriate, more precisely whether it preserves the characteristics of the interest. So as you can see that it contains many different points, and it's showing about the vertical averaging case as well. If you are interested, you can go into vertical averaging, and also it has some graphs to compare. But at the end of the day, really important part I want to really highlight here, which has a really strong business application, is threshold averaging. So vertical averaging has the advantage that averages are made from single dependent variable, true positive rate, and simplifies computing confidence intervals. However, and it points out the independent variables and false positive rate, it's not under the direct control of the researchers doing the performing the use cases. And it may be preferable average ROC point using an independent variables. The value can be controlled directly, and such as a threshold on the classifier scores. And after that, it is showing that let's moving into the minor limitations of threshold averaging with respect to vertical averaging. So to perform threshold averaging, we need to classify scores assigned to each point. So as the section 4.1 point out, the classifier scores shouldn't be compared across the model classes, because the ROC curves averaged from different model classes may be misleading because the scores may be incommensurate. And then these are problems with more than two classes. So when discussions are up to this point, we don't need two classes. Then much of ROC literature here maintains this assumption. ROC analysis commonly employed in medical decision making, in which two class like diagnostic problems like yes or no, presence or absence, or reject or accept. So abnormal conditions are common. The two axes represent the trade-off. So most important thing is a trade-off of between the two errors. So false positives, and benefits, which is true positives, that a classifier makes between two classes. Much of analysis is straightforward because the symmetry of exists in two class problems. The resulting performance can be graphed into two dimensions, which is very easy to visualize. So when it comes to multi-class ROC graph, it becomes a bit more complicated, but the same application applies exactly the way we do, and multi-class AUC as well. So when you talk about here, is touching on the interpolating classifiers. So sometimes performance desired of classifiers is not exactly produced by any available classifier, but lies between two available classifiers. Then the desired performance can be obtained by sampling the decision of each classifier. The sampling ratio will determine where the resulting classification performance lies. And there's example of this decision problem, which was depicted in this particular paper. So there in the challenge, they used a set of 4,000 clients to whom they wish to make new insurance policy. So budget dictates that, we can afford to market to only 800 of them. Then we want to select 800 who are most likely to respond to the offer. Here is a very practical example that actually can simulate how this theory and the methodology works, right? So the expected class prior of responders is 6%. So within the population of 4,000, we expect to have 240 responders positive and 3760 non-responders negative. So assume that we generated two classifiers, A and B, then score clients by probability they have to buy the policy in a ROC space. Let's have a look at the figure 10, so which is the drawn here. So false positive rate and true positive rate. And actually this example, the constraint line is showing like this. And then you are actually, this is how it's been calculated. The K is from A to C, and that's meeting the constraint line, and that's above. So let's look at how it's been continued from. So assume that we have generated two classifiers, A and B, which score clients by probability they will buy the policy in ROC space. A lies at 0.1 and 0.2 here, right? And B lies 0.25 and 0.6, which is this one, 2.5 and 0.6, right? And here it's saying that the ROC space, we want to market exactly 800 people. So our solution constraint is, false positive rate multiply 3760, which is non-responders here, plus true positive rate multiply by 240, which is the positives responders, right? And that gives us 424 candidates, which is too few. So if we use B, we expect 10,084 candidates, which is too many. So that's how we calculated we want to classify between A and B. The solution constraint is shown as a dashed line, this one here, and the C lies on it. So it intersects the line between A and B at C, so approximately 0.18 and 0.42. So the classifier point C would give the performance we desire, and we can achieve it using linear interpolation. So calculate K as a proportional distance that C lies in the line between A and B. So the conclusion is, so you can see that, how it's exploration approximating method. So you can get that the decision rate is at around 0.53. N aids decision at a rate of now 1 minus 0.53, which is 0.47. So that's the performance score. So in practice, the fractional sampling can be done randomly sampling decisions for each, and for each instance generate a random number between 0 and 1. So if the random number is greater than K, then apply classifier A to the instance, report its decision, else pass the instance to B. So for conclusion, the ROC graphs are a very useful tool for visualizing and evaluating classifiers. They are able to provide a richer measure and classification performance than scalar measures such as accuracy, error rate, error cost. Because they decouple classifier performance from class skew and error costs. They have advantage over other evaluating measures such as precision recall graphs and lift curves. So, however, as with any evaluation metric, using them wisely requires knowing the characteristics and also limitations. So it is hoped that article advance general knowledge about ROC graphs and helps promoting better evaluation practices in the pattern recognition community. So I hope this paper made sense. So today, actually, we ran through the structure and examples of what this paper wants to deal with and talk about in the ROC curve. Next week, actually, we want to go into practical use cases, so that how actually the theory works in real life and what medical use cases actually often use this ROC curve with the actual the numbers and actual the comparison examples. And I hope this has been quite useful because as I mentioned earlier, the ROC curve is very useful and practical because this is very important concept when you talk about when you're evaluating the performance of the model. And often it's discrete decision classifier, and often it is yes or no, accept or reject, or it's there exists or it doesn't exist, kind of the use cases and medical cases. But by creating the confidence metrics, actually you are presenting the threshold and giving the benefit versus cost the comparison, so that let business decide depending on the threshold they are willing to take. They can actually decide how much, where the performance, the rate you can apply for this particular the project, the model use cases for the decision making. So I'd like to pass it on to maybe Kainza to
Yeah,
see so because this is first time, so is that correct?
yeah,
So for week 4, normally we
yeah,
go through the narratives of the paper on the week 3, the first week, and then the
yes,
following week we actually get into deep dive, or we're using practical use cases
yeah,
and how the theory works in the real use cases,
yeah.
and then we really have a more deeper discussion. Is that correct?
Yeah, so for that, we also invited the one student from the Singapore Management University to present about his research. And then
Yes.
you also be there to web up all those things.
Fantastic.
Yeah. I think you are still sharing your screen.
Am I still sharing my screen?
Yeah, yeah. Could you please
Oh,
stop?
sorry. I didn't realize. I'm so sorry.
Yeah.
I'm sorry. I didn't realize I
Yeah.
was still doing that. Thank
Yeah.
you.
Yeah. Thank you
So,
so much, Angela, for like run through all the paper along. And so, so we still have 3 to 4 minutes to do the some Q&A question with
yep.
you and the audience, but I'm not sure.
Yeah. So I think, yes, I think the paper itself is, it's worth reading it, definitely, right? But the
Yeah,
most important thing is actually the next week is the highlight of this session, because now we read the ML paper, around this research paper around the ROC analysis topic.
yeah,
The most important thing is, because unless you want to be an academic and researcher, what we try to gain from this learning is actually the application in the business use case. And that's what we are going to do next week, because I am going to bring the ROC curve can be created by Excel,
yeah.
the graph, and also I'm going to show how it can be generated using Python scripts.
Ah,
And also I can show the actual use cases, how the decision making, how the threshold and benefit and cost can be decided by giving the balance and giving the options for business to decide, and how it can be used for the business decision making use cases.
yeah. Thank you so much. That's very really like went through all the paper. Thank you so much, Angela. So is there any question from the audience? So
Please pop through,
yeah,
and I really hope next week the
yeah,
use
because
case
this
can
week is
really
like,
highlight. Yep,
yeah, this week you are running all those the content. So maybe
correct.
so we can continue our discussion on the next week.
Yep.
So yeah, let me wrap up the question, our session. So
And
yeah,
and please also, if you can think of any questions after this session, please collect it, and you can actually pop through at the beginning of the next week, so that we can actually be mindful about answering those questions.
yeah,
And you can email us as well. So Kinza
yeah,
is kindly showing Women in AI email address here, which
yeah.
is y_apec@womeninai.co.
Yes, so our upcoming event we will announce very soon on our Women in AI APEC LinkedIn and Women in AI APEC Facebook. We also did recording for this session, and we will upload our Women in AI APEC YouTube channel. So is there anything related with this session and our event, feel free to send an email via apac@womeninai.co. I also would like to invite all of you to be a member of Women in AI. If you are not a member of Women in AI, please scan this QR code and you can register from that link. And also you can go to the womeninai.co website and can register on there. So for our upcoming schedule, as we discussed earlier, so for our next week will be the week 4 of our machine learning paper reading club, and will be on November 5, the same time. And at this in our next session, we invited one research student from the Singapore Management University, and half of the session will be explain about his research, and the half of the session where Angela will demonstrate the ROC analysis or around ROC analysis thing. So you can do, if you have any questions, you can send us an email or pop it in our session, and Angela can bring this and can answer your questions. So we also looking for the volunteer for the women in AI community. So if you are interested in those kind of positions, feel free to reach out to us and send it to our email, and we will get back to you. And thank you so much, everyone, for joining here today. And thank you so much, Angela, for hosting, be a lead on our session.
Thank you so much.
Yeah, see you in next session. And thank
See you
you so
next
much.
week.
Yeah,
Thank
see
you
you
so much,
next week.
Kinza. Thank you. Thanks, everyone.
Thank you, everyone.